Okay, good morning. We'll start. We'll continue our discussion on district algorithms. Sorry, not algorithms. All right. So last week we discussed the key idea of district algorithm. So today I will start with an example to see how it works. Then we'll formalize the algorithm, so put it into a pseudocode to describe the algorithm. Okay. So let's see how do we compute the shortest path from a single vertex S. So that's a source. So we start with this S. How does the district algorithm work? So as I have explained last week, each vertex will have a distance upper bound called the delta. So that's said to be distance upper bound. All right. Now at each step, we always choose a vertex of minimum delta. Then we'll enlarge vertices that have been visited and grow a tree out of S. Okay, yeah, it's a good question about negative edge. You will see, okay. Yeah, I see a private question about when the graph contains negative edges, what do we do? Okay, it's a very good question. We'll see, okay. So I intentionally put up some negative edges. All right, so initially, the distance upper bound will be infinity for all other vertices. So S is 0, all other vertices will be infinity. All right, so I will not put it in, all other vertices will be infinity. Now we pick a vertex with minimum value of delta. Of course, the only one is S because its upper bound is 0. Maybe you different color instead of this. To highlight it, so you all other will be infinity. So all the other vertices, the distance upper bound will be infinity initially. So I will ignore these things. All right. So first vertex we pick up, of course, is this the only vertex. Now, once we add this vertex to our set, so S, in the process we maintain a set S in visited vertices. So now for the counter situation, S is the only vertex inside this big S. So once we visited vertex S, then the distance upper bound of some vertices will be updated. Namely, those can be reached from S directly. So these three vertices with distance upper bound will be updated. All right. So distance upper bound of these three will be changed from infinity to 1, 2, and 4 respectively. So we change the distance upper bound to 1, here's 2, and here's 4. Okay, now we do same thing. Pick a vertex with minimum delta. So our grid method is the grid step. We pick a vertex with minimum distance upper bound and add it to S. So we enlarge the set of vertices being visited. Okay, so we follow this idea, and the vertex we pick will be, of course, this vertex because it's minimum value. Now we will also add this edge to the tree. So eventually we form a shortest path tree. Okay, so because we visit this particular vertex from S, so we add this edge pointing to this vertex. All right, okay? But once we include this vertex into S, the distance upper bound of some vertices will be updated, namely those that can be reached from this vertex by edges, by one edge directly. So namely these two vertices, the distance upper bound need to be updated. Okay, so This one is still remain to be 2. The one with infinity now be updated to 3. So these two vertices will change its distance upper bound. Now suppose this weight, instead of 1 is 0.5, then this 2, instead of 2, distance upper bound will be changed to 1.5. Basically, it indicates another way to reach this vertex. Instead of from S, we can reach this vertex from in this way. And this the distance it takes is 1.5. That's the meaning of delta V. I will give you exact meaning later. All right, but currently this basic idea, what the distance upper bound means. Sorry, this upper bound. Okay. All right, so this, sorry. I need to erase some, otherwise too messy. It's kind of slow. Okay, so this one updated, this one be updated to 3. All right. Now we do same thing. Now among vertices, we pick a vertex of minimum delta. So namely this vertex will be picked up. And we add this edge. The effect of this one will update the distance upper bound for some vertices. So this one will be changed from 4 to 3. This one will be changed from infinity to 5. I want to see, sorry, this one is not, sorry. I made a mistake here. This one is not, because arrow direction of arrow it's still, it's from right to left. So it's still same. So only this vertex, delta has been changed. All right. So then we do same thing, pick a vertex of minimum delta, so namely this one, since this one is added. And delta of this one is changed to 4. Now we pick a vertex of delta, minimum delta. So there are 2 with 4, so perhaps we pick up this one. So that will give us this. Okay. And maybe I don't use this negative weight in order not to confuse you for the time being. Okay. So maybe put it 0. Okay. Okay. So let's give you the idea, basic idea how Dijkstra algorithm works. Is it clear how it works? If yes, then I will go to the formal algorithm. We can put these ideas together and use pseudocode to formalize the algorithm. All right, so here is the algorithm. Then we can put it into an algorithm. So algorithm contains mainly 2 parts. One is initialization part, of course. That's initialization part. Initialization part usually is very simple. So only initially distance bound, only the source vertex is 0. All others will be infinity. All right. Now, initially, the set of visited vertices is empty, so no vertex has been visited. And the trees, as a tree, structured path tree also said to be infinity. All right. Now, in order to indicate tree edges, what we do is it's a tree. Eventually, what we get is the shortest path tree. So it's a rooted tree. That's tree T. All right. In order to record the tree, what we do is for each vertex, we need to know where it came from. So for each x, px denotes the parent of x. So we know that we use this edge to reach x. So the purpose of this parent is to indicate how we reach x, which edge we use. All right. So initially, the parent of every vertex is said to be nil. So nothing. All right. So actual value will be set up during the process. That's the initialization part. Okay, so that's very simple, but need to be careful, the boundary condition. All right, then we'll do it n times, because each time add one vertex. So their loop with n iterations. So the key step is the greedy step. We always choose a vertex with minimum distance bound. So what we do with enlarge this S, visited vertices will be enlarged by adding X. Of course, the tree edge, we add one edge to tree T. So that's this edge. We add this edge to tree T. All right. Now, other than this greedy step, the most important step is actually in the next step, the updating step. Because addition of this new vertex X, because of this path to vertices reachable from X by one edge may be shortened, because initially for each of these vertices there are distance upper bound. Each has a distance upper bound. That indicates how we actually have, that is the length of certain path. So maybe it's from S certain path. Actually, this upper bound is the length of some path. But now, because addition of X, there's an alternative way to reach these vertices. Namely, we can go through X and then reach these vertices. So then the distance may be shortened. Instead of delta, it can be, if we use this one, so maybe this one is shorter than that one, then we should use this one. So that's exactly what happened. So for each edge going out from X, we need to check whether we can take a path going through X. So that's the update part. We need to update the distance up bound of Y. So for original bound is worse than the path by going through X, then we update it. So this part is exactly, let me redraw it here. So particular vertex Y, here's X, all right. So that the distance upper bound delta actually means length of some path from S to Y. Now we consider an alternative, an alternative path that goes from X to Y. So length of this path is distance upper bound of X plus the weight of this edge, XY. So we compare these two. We compare this one with delta Y to see which one is smaller. So here's delta Y. So small one is better. So if this one is better, then distance upper bound will be reduced to the length of this path. So that's exactly what happens. All right. So update distance upper bound. And finally, this one indicates where the path comes from. So if it's updated, that means we're using this path. So that's why the parent Y will be this vertex. So we update it. So that's what happened inside the algorithm. Actually, it's very simple. The key step is really two steps. One is the greedy step. So here the greedy step. Sorry, the greedy step is here. This one is the greedy step. This one is the greedy step. And then the update part. Actually, the update part and the greedy steps. These are two most important ingredients in the Dijkstra algorithm. All right. Okay. So far, so good. All right. Now, of course, in terms of implementation, we need to be careful. There are some little bit very tiny problem here. Actually, one thing is here. This one. technically a little bit strange. So when we add S in the first iteration, so what we add for S, actually it's okay. Maybe in the notes there's a small typo. I correct it. So in the notes we add this one, the first step. So in terms of implementation details, there's a tiny thing here. You need to just need to be a little bit careful. We add this one as an edge, but this one is neo S. So it does not really look like the edge, right? Because actually it does not matter. You can add a loop, but then you will say it's not an edge. So if we, technically speaking, if we really do it this way, we cannot say T in a tree because there are this strange thing here. But what we can do in terms of implementation, we can eventually remove this one from T, remove this strange thing from T, then T is, afterward, we can remove it. Then T is really technically is a tree. But that's very tiny thing, okay, in terms of technicality, okay. Now, in terms of implementation, what we can do is, in order to implement this one very quickly, what we need to do, a couple of things we need to notice. We need to choose a minimum element. Secondly, the key value may be changed. So the key value may change. We need to pick up a minimum element, select the minimum element, and the key value may be changed. So a proper data structure for this kind of operation is heap. In order to implement this one quickly, we can use heap data structure to do it. So if we put that together, what happens is the following. So let me give you just a key part. So you're talking about implementation, we can use the queue, priority queue. So heap, a priority queue, okay. We use priority queue for vertex set in terms of implementation. And you key of this priority queue will be delta of vertices, delta of a vertex, the distance upper bound. All right. So once we decided to use a queue, so what happens is the algorithm, the main part, look like this. So instead of using for loop, we can check whether queue is empty or not. If not empty, so there are still some vertices that have not been processed. So select the minimum element. We can use delete minimum operation for the queue. So that allows us to select the minimum element. Then for each edge, update part, we just check if y is more than x plus weight of xy, then we update it. All right, then the key value has been changed. We should say decrease key QY. So that's the implementation detail if we use priority queue. Here we only compute distance. I don't care about the actual tree. So in order for sake of clarity, so here I only compute distance. So this part tell you how to compute distance. You can add adding edges to T part by yourself. It's quite straightforward. So here, for clarity, I only show you how to deal with distance using priority queue. All right. So it's quite simple. So two operations, delete, minimum, and decrease queue. Two operations for priority queue. Of course, now we need to get into TDS details of how to implement priority queue. That's abstract data type. That's abstract data type. So it's a set of objects plus operations. So these operations we need to carry out. There are many actual data structures supporting priority queue. For instance, we can use binary heap. Priority queue, we can use binary heap. So using binary heap, each operation costs log n time. Both of them cost log n time. So then different algorithm can be implemented in m plus n log n time. If we use binary heap, actually we can improve time from this one to order m plus n log n using a different kind of heap, a more complicated one called Fibonacci heap. All right. Many years ago, when I taught this structure, I discussed Fibonacci heap. It's a little bit complicated. We're not going to discuss it. You can just use it. By using Fibonacci heap, the time can be reduced from n plus n times log n to m plus n log n. So it's better. All right. Okay. So this gives us enough details for the Dijkstra algorithm. From the pseudocode of the algorithm, this one, to some details of implementation. So here are some details of implementation. The key idea is really two parts. The minimum, the key part in grid step here, and updating part. That's the key part of Dijkstra algorithm. Okay, sorry, I don't understand the question. What's a big O operation or big O? Yeah, I see a question, but I don't understand your question. I don't see your chat message actually. Oh, that's total time. That's total time. Okay, big O, that's total, that's the complexity of algorithm. Running time of the whole algorithm. That's the running time of the whole Dijkstra algorithm. Okay, not a number of operations, total time. So Dijkstra algorithm runs in m plus n log n time by using Fibonacci heap. All right. Okay. All right. Now we going back to the example to see if it really works. All right. So it seems it makes sense and it should work. And we have an algorithm and also implementation. But it really work. All right. So so far we computed part of it. So this part is S. That's big S. And the waved edges are trees. So waved edges. This indicates tree T. All right. Okay, so let's take a look. So far so good. So what we need is, so actually, sorry, it's slow. Okay. So basically what we need is for every vertex inside S. So for this vertex, what we want is a distance shorthand. So, okay, just use this one. So shorthand for this one, last time I mentioned, we just use DV as shorthand for DSV, okay? So shorthand. So what we want is distance of each vertex inside S is computed. So then the tree, the unique path from S to that vertex in T is a shortest path. So that's what we want. So by saying that dv has been computed, actually what it means is distance upper bound is set to be its distance. So that's what it means by distance has been computed. All right. So currently we computed 4 verses. For these, it seems to be okay, right? So this, if we just look at this part, so distance of this vertex is 1, distance of this vertex is 2, this one is 1, this one is 2, this one is 3, and this one is 4. So if we look at this part, it seems to be all right. However, let me just mark this vertex as maybe so A. Okay. So if you look at this picture, that dA equal 4. And this one is shortest path from S to vertex A. But if you look further, you will see that actually distance of D from S to A, DSA, actually is not 4. The actual distance, this one actually is not 4. Actually is -2, because there's this edge here. So actual shortest path to the to vertex A is actually through this. Do you see it? So what we want is, in the process, we want this one. Dexter algorithm, if we use Dexter algorithm. However, it causes a problem because it does not really compute distance in this way. Because for vertex A, we have a problem. So once we have this problem, actually, even distance from S to B, so DSB actually is not 2. It's also -2, I think, right? So actually, it's also maybe DSB is also -2. So because shorter path actually goes this way. So what does that mean? That means the Dixie algorithm actually does not work correctly. So what is wrong? So actually that means 2 things. So one is, yeah, good question. What does negative edge weight physically means? You will see it after the break when we talk about applications. It's natural. It's not unnatural. All right, I discuss it then. Okay. Now, 2 things. One very important. Dictionary algorithm only works, not only works. It may not work when edge have negative. When some edge have negative weight. It works correctly when all edge weights are non-negative. It's very important. Normally, you may forget this part. It's really very important. It's only guaranteed to work correctly when all edge weights are non-negative. No need to be all positive. Non-negative will be good enough. All right. The second thing is it may not work. when there are negative edges, it may not work correctly. It still may work. It depends on the structure of negative edges. All right. So it's very important to remember that dictionary algorithm only works correctly when all edge weights are non-negative. That's very, very important. It does not works always works. It does not always work. All right. So what does it mean? We really need a proof now. Dictionary algorithm works for this case because it's getting subtle. Otherwise, it's obvious, and perhaps we don't need to put too much effort in the proof. But now it's become subtle. It's not clear at all whether it works, right? Because if you look at the previous example, so initially we thought it works, but then we find it actually does not work correctly because of this one. So that's really cause for proof. We need to prove it that this algorithm works when there are no negative weight edges. All right, so it's really cause for proof. So what do we need to prove? So one thing is we prove that the following. Actually, we again prove an invariant. It's very important to prove something that is always correct in the whole process. So it's called invariant. All right, so we need to prove two things. Actually, one thing, okay, that's what we want to prove. But in order to prove this one, we need to prove something else because that's not enough. We need something stronger at any time. For every vertex inside S, its distance equals its distance upper bound. That's what we want to prove. If this one is true, then when the algorithm terminates, we have visited all vertices, then of course we find the distance. Then it's computed correctly. However, in order to prove this one, we need something else. It's not easy to prove this one. So in order to prove this one, we need a B. The value of distance upper bound is not set to be an arbitrary value. It has some meaning. So that meaning is this one equals all right, or delta x, yeah. Thank you, yeah, it's delta x, of course. All right, so what does that mean? So we have a set of visited vertices. So that's S. That's visited vertices, a big S. And that's small one, okay. So that's source, all right. Now for any vertex X, so delta, this value is said to be actual length of shortest path from a source to this vertex, but going through some vertex inside and jump to S. So it's only include one edge to S, X. So this distance bound actually is the shortest such path, length of such shortest path. So all other vertices of this path are inside S. X is the only vertex outside of S. So that's the meaning of this step. Actually, it makes sense when we set up this distance up bound. When do we update it? When we include a vertex. When we include a vertex, we update distance for these vertices. So when we visit this vertex, that means this vertex will be put inside S. So when we include this vertex inside S, we update distance up bound for these vertices. So you see, for these vertices, it's also indicates a path whose internal vertices are all inside S, except the vertex itself. So that's meaning of distance upper bound. So in order to prove A, we'll need B. So what we really need to prove is A. But it's not easy to prove this one at all. In order to do that, we need a B. All right. So that's what we're going to prove. Of course, and use induction. We need to prove A and B always holds. Induction hypothesis, of course, before we add a new vertex, A and B holds. Then we need to prove after we add a vertex X, A and B still hold. All right. Okay. So let me see. Yeah, perhaps just enough time before the break. So let's see. So what will happen is we add a vertex, a new vertex, X to set of these vertices. All right. So let's see. So consider shortest path. All right, so we have source here. So this source. Here we have set of visited vertices S, and then we add one new vertex X. So this new vertex is added. Consider shortest path. If the length of shortest path equal delta X, then we are done, of course. Because distance is set to be the length of shortest path, then it satisfies the property. All right. So in case it's not, we'll see what other shortest paths look like and what's the relation between P and the other path. Now, so P may go through, will go through some vertices here and maybe come out, then going again, maybe it's possible like this. All right. So regardless of how the path look like, if every vertex here is inside S, then it's done. So if all internal vertices of P, if it resides, then by B, we are done. By property B, because this one is length of shortest path from S to X, whose internal vertices all reside inside S. All right. So if it's not the case, there are a vertex that's not inside S. So let X prime first vertex. Not inside S. So we have this situation. All right. Now the path will be broken into two parts. One is from S to S prime, and another part is this part. Sorry, suddenly it's delayed. Okay. Another part is this part. So let's denote this part by P prime. So situation look like this. So what we have is dx. So the length of this path equals distance from this vertex S to X prime plus length of P prime. All right. P is the shortest path, so its length equal the first part plus second part. So that's first part, that's second part. So addition of these two. All right. Now, here's the key observation. What is this one? This one is delta X prime. Because of property B, suddenly something changes. Oh, okay. All right. Because of property B, dx prime equals delta x prime. Because for this vertex, all internal, for this path, all internal vertices are inside S. So meaning of delta is exactly the length of path, shortest path from S to X prime, whose internal vertices all reside inside X. So therefore we have this one. So that's very most important observation. dx prime equals delta x prime. All right. Now here is the reason why Dixit algorithm works correctly. Because all edge weights are non-negative. So that means this one is non-negative. Because all edge weights are non-negative. So we know then length of this part is non-negative. This part may be 0, but it's non-negative. So that means this one is at least delta x prime. All right. Now, why do we choose vertex x instead of x prime when we add the next vertex? Is because delta x is no greater than delta x prime. We choose a vertex with minimum delta. So therefore, that means this one, delta x prime is at least delta of x. So that gives us the relation delta x at least, d of x is at least delta of x. So distance is at least its distance upper bound. Now, as we said earlier, delta is the distance upper bound. So we already knew we have this inequality. Also by B, we always have this. So these two together implies distance x equal delta of x. All right, so indeed, A is satisfied. All right. So now we can also prove B. B is also easy because what happens when we update, when we add a new vertex? So for these vertices, we update it. So for these vertices, say y, delta y is updated to delta x plus xy. That's exactly what is required for B to hold. So therefore, it's also, from this one, it shows, also shows B holds. So here means A holds. So these two together means indeed it works correctly by mathematical induction. So indeed A and B both holds. All right. So therefore Dixit algorithm works correctly. All right. Okay, I think yeah, it's just time. We should take a break, and after break, we'll discuss what do we need to do when graph contain negative edges. All right. Okay, so let's take a break.